Okay, I'd like to talk this morning about an aspect of infrastructure that's either at the very upstream end or the very downstream end, depending on your perspective. The view here is the property view. So if we look at the water supply system, this is clearly at the very downstream end, and if we look at the drainage provision, it's the very upstream end of the system. But the focus is definitely here on water supply and drainage, and the focal point really is water use at the property level. Most of what I present this morning is based on the work of my colleagues and of the research group. So I would like to acknowledge that and a few acknowledgements at the end as well. But I think in terms of presentation, what I'd like to cover first of all is the research scope. So collectively as a group, what is it we actually do? And then I'd like to present to you 3 examples: water conservation, drainage diagnostics and climate change. 3 examples of particular pieces of work that we've done that I think will be industry relevant and hopefully of interest. So scope first of all. What we cover within the group mainly is the provision of potable water and the disposal of wastewater. The tools that we have available to us to be able to do that are encompassed here. So what we have are models that allow us to look at drain line simulation. Now, at the very small scale, at the property scale, the defining characteristics of the flow are definitely unsteady. They're very transient, so they're unlike the flows that you find in large-scale sewer systems that are much more steady. So we need to be able to understand the wave attenuation properties of the flow, and that then lets us predict solid transport inside the system. And from that, we can look at drainage design, for example, for low-flow appliances. Big push at the minute for water conservation. What are the implications of that on drainage design? And one other thing that we do is we look at flushability criteria. So in terms of what we can actually enter into the drainage provision, what's a permissible solid that we would be able to remove from the property-based system. Second aspect is in drainage ventilation. Many people think that drainage is really about removing water and wastewater. One aspect that's often forgotten is ventilation in a drainage system. So we look with our models at the changes in pressure, the changes in transient pressure in the system, and how we can control those, where the main aim is to make sure that we retain the trap seals, to protect the integrity of the trap seal, so that we don't have any cross-contamination between what's on the drain side and what's inside the building. So again, we look at system design from a ventilation or an air perspective rather than a water or wastewater perspective. And then the third tool that we use is around rainwater and climate change. Here in terms of rainwater, because we're at the property level, we're looking at systems that cover conventional and siphonics. So siphonics you tend to find on bigger buildings, for example, large retail buildings on the outside of town. Completely different characteristics in the way that they respond to their conveyance of water. So we need to understand the issues that are encompassed within the provision of those systems. And for siphonic systems in particular, this surrounds issues such as system priming, system transients, and the way that pressure changes affect the performance. And as Jim mentioned earlier, climate change impacts on the way that we convey our stormwater. And I'll make reference later to our use of UK CP09 DEFRA-funded data. And finally, we also look at outlet blockage and maintenance issues, because the as-designed system seldom performs in the way that you think it will. The in-situ performance is frequently very different, so we do need to understand where that shift in performance comes from. So the tools we use then, the common theme, if you like, is numerical modelling. That's fundamentally what we do as a group. We model all of these systems together. That allows us to look at the stormwater, the water supply, and the waste and vent systems in drainage provision. We have 3 numerical models that are based around the same techniques that we use to do this, and they refer to as DrainNet for the water side, AirNet for the air side, and RoofNet for all of the stormwater and the rainwater conveyance. Those are all one-dimensional finite difference models, but we're also trying to extend that into CFD modelling to look at a bit more detail at some of the flows around, in particular, some of the junctions. So the first of 3 examples then, water conservation, clearly an important topic at this time, and it's been mentioned a number of times this morning already. When we look from a property perspective, we're looking fundamentally at what we call domestic usage. Now, that's not necessarily domestic buildings. This does encompass commercial and industrial buildings as well, but does focus on what we refer to as domestic consumption. So this is essentially potable water. And a drive now for water efficiency and to use less water within the property and to use it better as well, so not only about using less. Lots of changes have had an impact and an effect already on how much we use, and if we can go back to 1999, we had, I guess, the first major change at this time, which was the introduction of the Water Regulations Water Fittings Act. And again, we have mentioned this morning, the change in WC flush volume previously had been of the order of 9.5 litres per flush. WC, as you probably know, accounts for around a third of all water used within domestic properties or under the heading domestic consumption. The 1999 Fittings Act changed that in as much as that new devices now are limited to maximum flush of 6 litres. So quite a big impact in terms of the amount of water that's used within the property. And slightly later in terms of timescale, we've seen that reflected in England and Wales in the Code for Sustainable Homes and in Scotland in Section 7. Of course, we also have the Draft Water Bill 2012 and the Water Resources Bill 2012 as well, within a Scottish context. Lots of drivers for water conservation. Not all of the regulations and the advice that's given necessarily will work their way into the design. So these are not mandatory regulations or schemes that have to be adopted, but we are seeing a shift in the overall consumption levels. It does have an impact on the supply side, and it has an impact on the drainage provision as well. So what does that actually mean? How do we, Jim talked about how do we understand what the implications are? And I guess one of the things that we need to understand are what are the new loading characteristics for the supply and for the drainage. At the minute, if you look at designs, you'll see that both of those things, the loading and the demand characteristics, come from work that was done in the 1940s. And although that work is still very, very valid, the physics still apply, the engineering principles still apply, the way that we actually use appliances and the amount of water and the way that we use our water for different purposes within the property has definitely changed. And the standards and codes haven't really kept up with those changes. So we do need to rework the demand and the discharge units and our application of those in design of systems. One further thing here is that there is a perception in some quarters that if we reduce our water consumption too far, we end up with our drainage provision being so low in terms of flow rates that we have a phenomenon called dry drains. It's a rather unfortunate terminology because it's perceived slightly negatively. The argument that we have within the group is that if you design properly and you understand your loading characteristics and the change in consumption levels, then dry drains is not an issue. So we would argue that avoiding dry drains is something that can be designed out and should not be a reason for not implementing water conservation measures. So what does this mean in practice then? If you look across the range of appliances that we use, we've mentioned the WC is the main consumer, and that's a very important one on the overall scale, not only in terms of volume, but in terms of the transient characteristics and the flow that are subsequently introduced. We need to look across all appliances and how the change in consumption and user behaviour affects the demand loading and the discharge loading. And then together we can look at an assessment of the combined flows and new ways in which we can use that assessment to design systems so that we understand the implications of the supply and the drainage together, so almost an integrated approach, if you like. We are trying to avoid dry drains, but we're also trying to make sure, for example, in the supply side, that the velocity in supply networks doesn't drop so low that you have, for example, biofilm issues. So those are the kinds of challenges that we want to make sure we can address. We don't want to introduce new problems by solving current problems on consumption. The second example is around what we've loosely termed drainage diagnostics, and this refers to the ventilation provision in essentially building drainage systems. So I mentioned earlier that building drainage is not just about removing water and waste products from the property, it's also about ensuring that we have adequate airflow inside the system. And it's not commonly known, but we have as much as 8 times airflow as we do water flow inside the drainage system. That results in pressure changes inside the pipework that have to be accommodated, and pressure transients are our main concern. So steady state pressures are much easier to deal with, but rapid changes in pressure are much more difficult to manage. And it's those rapid changes in pressure that cause the loss of trap seal and potential problems in the overall design. So all of this essentially is driven by work in water conservation. What happens to the pressure change when we change the characteristics of the appliances that we use? Are we still able to protect the internal space in our buildings and not have loss of our water-based trap seal? The water-based trap seal is most frequently lost through negative pressure, and we understand those mechanisms quite well. But we also have positive pressures in systems too. Those generally occur at the base of stack where you have, for example, surcharge conditions or design conditions that mean you have the conveyance of positive pressures through the network. We need to be able to design for positive as well as negative, and I guess in terms of development, the positive pressures have taken longer to work out in terms of design than the negative pressures. But we have here, through the work of the group and using the numerical simulation tools that we have available to us, we've managed to design systems that accommodate both the negative and the positive. So we have, particularly in terms of positive, we developed here at Heriot-Watt the device called the PAPA, which is Positive Air Pressure Attenuator. And fundamentally, it slows down the velocity of the transient, the positive pressure transient that's generated within the system by absorbing it within this device that you see in the bottom right-hand corner here. So this is a device that's now marketed. It's able to be used, or is permitted to be used by standards both in the UK, Europe, and indeed internationally. And you see in the middle photo an example of its use in a high-rise building in Hong Kong, where the particular conditions there that arise from high-density living mean that the propensity for surcharge at the base of the stack and the sewer collection system is quite high. And the reason we have the photo on the left-hand side is because we did have some video footage of the effect of some positive transients that meant you could actually see the water trap seal move inside the WC bowl, and that movement was quite significant and clearly quite worrying if you're in one of those lower level apartments. So the installation of the PAPA devices, this is this now commercial product, the installation of those two devices fundamentally absorbs the positive pressure at the base of the stack and means that those problems can be alleviated. So it's essentially a diversion and a device that allows the wave to slow down. It's then released belatedly, so in the system over time we can release that positive pressure back into the system and fundamentally acts as a safety device to protect the trap seals in the building. The work that came subsequent to that, and again I'd like to mention commercial product, but the work that came subsequent to that came from the very high profile cross-contamination event in 2003, which was again unfortunately based in Hong Kong and was centred around the outbreak of SARS, again high density living, and a number of cases within a high-rise building. And lots of work was done on tracking the distribution of the virus. And what was found that it was a very prominent vertical distribution that was quite quickly actually attributed to the drainage system. That fundamentally is, I won't go through the whole story, but for that fundamentally came from trap seal depletion. And what we were finding is that the virus was moving through depleted or empty trap seals in one apartment. It was then moving vertically across or upwards in the building and being passed to other residents on upper levels, and this is what gave this very strong vertical distribution of the disease at that time. Now the usual aim is to suppress negative transients, and that not necessarily in the SARS case, but that would have prevented in many cases depletion of trap seals. So we tend to focus on suppressing transients, but we did realise that if you were able to detect cases where you had dry trap seals, for example, in this Hong Kong building, then you would be able to remedy this without the negative consequences that would come should there be an outbreak of any disease that could be transmitted in that way. So the device that was developed again on the work and the modelling that we've done here at Heriot-Watt was looking at, this time deliberately introducing a pressure transient to the system, and in this case happened to be a sinusoidal wave that was introduced. And here the theory is that if we introduce a very small scale pressure transient to the system, convey that through the network, it will then detect and locate the dry traps in the system and feed back to a central point that would inform, for example, your facilities management team that would then be able to go and remedy the situation. So this device is essentially a non-invasive, non-destructive device, transmits a very small sinusoidal wave through the system and picks up either a +1 reflection or a -1, those corresponding to either a closed end or an open end. And if you actually measure the time the wave takes to go and come back again to the point of measurement, you can actually identify where the defective trap is, and that allows your team to go and fill the trap, and that would have averted, had it been used in Hong Kong, it would have averted the cases where we would have known where the empty traps would have been. This graph just shows an example of the trace that we would see when this comes back to the diagnostic system, and shows quite clearly the deviation in the traces. The fundamental theory or the underlying theory in this is that you always have a defective-free system, so you do need a comparator to be able to benchmark against. That means that once you have a defect-free trace, You would then run, for example, a trace every 24 hours, sometime during the night when nobody's using the system. Compare with the original design, you see the defective point, the time scale of the wave travel will tell you where the defect is, and then you can then go and remedy that. So that's the fundamental theory, but that allowed us to develop, and this is the industry context here, that then allowed us to develop the device again that is now a commercial device and is marketed internationally. We tested this on a number of buildings just to make sure that we had the theory correct and that it was actually telling us where the defective traps were. So a number of large and smaller scale buildings, and always checking the diagnostics to make sure that the location in particular was correct. And you can see on the right hand side here an image of the device with the connected manifold to the various systems that were being tested. So the third example, and I guess this relates quite closely to what Jim Conlon was talking about, is the rainwater and climate change work that we do. So jump topics slightly here, in that we're now dealing with rainwater-only systems and looking at the conveyance of, and we've referred to the upstream end of the scheme, the conveyance of stormwater from the property into the main urban network. The scope of the systems that we're looking at, again, just to reiterate, we have conventional rainwater systems. They're located on or around the building, and also siphonic rainwater systems, which have a much closer design scope. So they tend to have a fairly fixed design capacity and don't have much flexibility to be able to accommodate the impacts of climate change. We also look at surface runoff from local ground areas, and we can add all of these together. We can then link with, in the cases where they are linked, we can link with the building drainage networks where we have combined systems. And together what that allows us to do is to model all of the flows at the local, or what we would term the small scale underground drainage network. And to then, and I'll talk you through, to then look at the impacts of climate change on any decisions that you might change, any decisions that you might make that would be designed to either alleviate flood risk or to build resilience against climate change. So the kinds of problems that we might anticipate would be, for example, the undercapacity of the roof drainage system, and in a conventional system that would lead to overtopping, and you can see the water spilling over the gutter. Clearly the subsequent problems are based around moisture penetration and flood risk within the curtilage. For siphonic systems, the same type of problem occurs. You can also have undercapacity that leads to overtopping, but in this case you have different types of problems manifest, in that the system, because it's full bore, behaves in a different way. So you have a very cyclical response sometimes that can cause lots of noise and vibration in the system and can undermine the performance. We also have, in some cases, blockage due to dry weather, and you can see in the middle photo here an example of some blockage around a siphonic outlet. That, in this case, the maintenance programme is not too bad, but you can see clearly there are some maintenance issues with this outlet. And then finally, we can look at surface runoff and again, the small-scale local areas. So we can look at the difference in runoff between hard-standing and pervious surfaces, and the balance of those two within the curtilage, and how they connect to the conveyance of rainwater from the roof of the building. So quite fortunate in that we have a building local to campus that we've been able to use to look at all of these things together. This is the National Archives building in Sight Hill. And what we've done here is we've instrumented all of the building, the roof, the systems, and we've also modelled the surrounding area within the curtilage that lets us look at the overall, the integrated property drainage, if you like. The two top and the bottom left images here are also from the same site, and you can see the impact of accumulation in the gutter here. Again, the maintenance regime is fairly good, but the build-up we found in the gutter does happen quite quickly. And this is one of the cases where the in-situ performance is quite different to the design, or the intended design performance. The bottom right is a completely different system. It's actually based in the west of the country, and is from a university building, but clearly you can see that this is not how the outlet is supposed to be used either. So there are some in-situ problems that we did come across that caused that design point to shift as well. So the way that we tried to understand the climate change impacts on that small-scale system was by looking at the output from the UKC P09 probabilistic climate change data sets, and using the weather generator to form benchmark data sets against which we could measure a threshold for the system. So as in all cases, again, Jim talked about it, we need a design storm. Conventionally, you would identify a return period that you would use to design these systems. We also need a design storm to run through the numerical model. So we're looking at mainly precipitation data from climate change data sets, The scale of what we used from UK CP09, and you probably recognise the terminology, but emission scenarios, low, medium and high, and the time scales 20, 40s, 60s, 80s, and then for those of you that are familiar with the probabilistic terminology, the 10th, 50th and 90th percentiles compared with the baseline data for climate change, the 1961 to 1990 data set. That then allowed us to use the weather generator, which is a component of CP09, and to look at the hourly precipitation design storm event. Now, the design storm event that we had to use was an hourly basis, because what we found is that the weather generator only had a resolution of 1 hour. So again, those of you that have used the weather generator, it's freely available, will find that that resolution can be limiting. Again, if we come back to return period, we have the issue of return periods being different for the building and the local area. So buildings have a much higher return period of the order of 100 years, whereas the local drainage can be designed as low as 30-year return period. And Jim's question was, if we account for climate change, how does that return period change? And unfortunately, there is no one single answer to that. But what we've been able to do is define a common event that allows us to bring these two different design approaches together to then test the building for resilience by identifying a failure threshold and then running that in comparison to the data sets from CP09. And what that does then is that allows us to look across these timescales and emission scenarios, to look at the low, medium and high and then the 3 timescales, and to identify the difference so we can tell the property owner how many more times the building is likely to fail under a particular emission scenario. And where that then leads to, which is the final stage, is to allowing the building owner to make decisions on adaptation options. And there are a number highlighted here. Clearly, you wouldn't want to implement all of these. So the types of examples that we have here, changes in design or configurations, pipe sizes, diameter, gutter sizes and layout. You could implement a green roof if that's what you chose to do, fairly significant change. Rainwater reuse, permeable surfaces has quite a big impact. And if you really wanted to, you could put in an offline storage system. But many of those are quite costly, whereas some are not. Some can be implemented at design stage and some can be retrofitted. So what we wanted to do was to use the climate change output data from the model to be able to help prioritise these adaptation options. And this is where we got to at the end of the project that Gary mentioned, is we're now able to say to a building owner, the main priority for you is to avoid flood risk or to build resilience in your system. And the best way to do that is to adapt under climate change scenarios to one of these options that has a practical basis as well. So we don't necessarily go for the lowest threshold. We want something that's a practical and cost-effective solution for the building owner as well. So all of that work was wrapped up in the downpipe project. Those are the 3 examples that I wanted to run through for you this morning. And once again, I'd just like to acknowledge the contribution of the team. It's not just my work alone. There are about half a dozen of us all together. So hopefully that's given you a flavour of the kind of things that we do within this group that try and address some of the hydronation challenges. Thank you.